Hey guys, in the previous concrete structures video, we have learned the concepts in design of bond, shear and torsion of RC beams. Now in this video, we shall see the design of RCC beams by limit state method, how to calculate the moment of resistance and what is the formula, how IS 456 we have to follow the classes and sections. Now let's get into the first question. The maximum strain in an extreme fiber in concrete and in the tension reinforcement in a balanced section at limit state of fracture are respectively. Here they have asked the value of maximum strains of concrete fiber, extreme fiber in concrete and in tension reinforcement in a balanced section. What is meant by balanced section? The depth of neutral axis is equal to exu limit, that is the balanced section. So here the option is option A, 0.0035 is the maximum strain in extreme fiber in concrete and 0.0038 for tension reinforcement. Now let's see how it is found. We know that the maximum strain in concrete shall be 0.0035 as per IS 456, and in case of reinforcement it will be based on the grade of the reinforcement material. Here they have mentioned as Fe415, so just substitute Fe415 in this formula, that is a strain extreme fiber strain of tension reinforcement shall be given by Fy by 1.15 ES plus 0.002, or we can say 0.002 plus 0.87 Fy by ES. 1 by 1.15 is equal to 0.87. So 0.87 into 415 divided by what is ES here? ES is Young's modulus of steel, that is 2 into 10 power 5. These specifications of material shall be dealt in this video, suggested video of summary of IS 456. You can see this video also so that you can get a clarity about the properties of materials as used in IS 456. Now just substitute 415 as Fy value so that we can get the answer as 0.0038 as the maximum strain in extreme fibers for steel reinforcement. And for any grade of concrete, the maximum strain at extreme fiber in concrete will be 0.0035. So this will be as per IS 456 2000. Now let's move on to the second question. Consider the singly reinforced beam section. The stress block parameters are as per IS 456. The moment of resistance by LSM method is. So they have given a beam having cross section 200 cross 300. 300 is the effective depth, 300 mm, and they have mentioned four numbers of 12 mm diameter bars of Fe415, and the concrete grade used here is M25. So using IS 456 codal provisions, we have to calculate the moment of resistance. Here the answer is option C, 42.77 kilonewton meter. Now let's see the calculations and the formula used. So first we shall calculate the AST, that is area of steel reinforcement. So pi by 4 into d square into 4 numbers. So that will give answer as 452.38 mm square as the area of steel reinforcement. And we shall find the exu limit, that is the neutral axis for a balanced section. So exu limit is equal to 0.48d. So this formula is also got from IS 456 for Fe415. In case of Fe415 tension reinforcement, exu limit will be 0.48d. So here d is the effective depth, that is 300. So 300 into 0.48, 144, that is 144 mm. And as per the given section, what will be the XU value? That we have to find by using this formula, or the relation XU is equal to 0.87 Fy AST by 0.36 FCKB. So we know Fy, that is 415, and AST is 452.38, and FCK is 25, since the grade of concrete mentioned here is M25, and B is the width of beam section, that is 200 mm. So substituting all the relevant parameters here, we get the answer as XU as the answer as 90.73 mm. So compare this XU with the balanced section. So here we see XU is less than the XU limit. So that means the section is under reinforced. So for under reinforced section, we shall use these two formulas, one of these two formulas, so that we can get the answer for moment of resistance. In case we have to consider the concrete properties, we can use this MOR. Moment of resistance is equal to 0.36 FCK BXU into D minus 0.42 XU. So we know all the parameters here, FCK BXU. So on substituting all the things over here, we can get the answer for MOR, that is moment of resistance, as 42.77 kilonewton meter. Or we can use this formula also with respect to steel. 0.87 into 415 into AST is 452.38 into D minus 0.416 XU or 0.42 XC. So D minus 0.42 XU is the leave around distance. So on multiplying that with the force, we can get the answer for moment. So these are the way to determine the moment of resistance XU for a under reinforced section. Now we shall move on to the next question. Let's see the third question. Assume straight line instead of parabolic stress strain curve of concrete. So in this second question itself, we have seen the stress block parameters and stress varying. As per IS 456-2000, the stress is varying here as a parabolic. But in this question, they have mentioned to assume as a straight line. They have given some particulars about the beam. Use partial safety factor as 1. The beam size is given as 300 mm cross 500 mm. The reinforcement bars are used as 3 numbers of 16 mm diameter of grade Fe415, and the concrete grade is given as M20. Our job is to find the depth of neutral axis. So here we cannot use the direct formula, that is x is equal to 0.87 FYAST by 0.36 FCKB, as we have seen in the previous question, because it is not as per IS 456, since the variation of the stress is straight line, not parabolic. So that's why we have to arrive the or derive the formula to get the XU. Now we shall see how we can get that. Here the answer is option B, 76 mm. Now we shall see what is the approach to get the answer. Consider this point as A, this point as B, and this point as C. So by using the similar triangle or the property of triangle concept, we can get the AB by AC as 0.002 by 0.0035. So here we know the strain value, here we know the strain value. So AC by AB or AB by AC is equal to 0.002 by 0.0035. So that means it is 4 by 7. So we know AB by AC is 4 by 7. Then what is BC? 3 by 7 XU. So what is XU? The total depth. That is the XU. That is neutral axis depth from the outermost compressive fiber. So upon moving to the calculation of compressive force, we have two blocks. One is rectangular variation. Another one is triangular variation. So for first, let's calculate the rectangular variation. So 0.67 FCK into breadth of the beam into the depth up to the rectangular variation, that is 3 by 7 XU, that is nothing but BC value, right? So we calculated this C1, that is the compressive force in the rectangular variation portion. Next we shall see the triangular. So area of triangle is half into B into H. So half into B, here is 0.67 FCK into breadth of beam into H, that is 4 by 7 XU. So upon simplifying this equation, we get like this, 0.48 FCK BXU. And for total tensile force, here we can see 0.87 Fy, and it is not varying, like it is similar to the IR 456 codal provision 0.87 Fy. So then what is the tensile force? 0.87 Fy into area of tensile steel, that is AST. So at the neutral axis, the compressive force and tension force will be equal. So on equating both the things, we can get the answer for XU. So XU, we can get the answer as 76 mm. So on just substituting the value of FCK, B, Fy and AST, we know all the things, right? FCK, B, XU, Fy and AST. On equating these two equations, we can get the answer for XU. So this is how we have to calculate the XU value, that is the depth of neutral axis, when we are considering other stress block variation. Now we shall see some more points regarding this. So y1 and y2. What is y1 and y2? Y1 is uh, the point of compressive stress acting by the rectangular block. That is this 0.36 FCK BXU, right? As per IS 456. So where it will be acting, that we have to find as y bar. So that so we have to find y bar. Uh, to find y bar, we have to calculate y1 and y2. So that is the y1 value. That is for rectangular block, the centroid of the rectangle section is half into 3 by 7 into x. That is half into the depth of the rectangular block. So by using that concept, that is centroidal RCG concept, we can get the y1 value as 3 by 14 xu in this problem. And similarly, y2 is nothing but, for example, this is the rectangular block and this is the triangular variation, right? We have to calculate y1 up to this centroidal distance and y2 for this centroidal distance. So y1 is nothing but half of the height of the rectangular block, that is half into 3 by 7 xu. And similarly y2 is this height of the rectangular block plus this centroidal distance of triangular section. So that's why 3 by 7 xu plus 1/3 of 4 by 7 xu. Why 1/3? Because it is from the base of the triangle. So that's why 1 by 3 into 4 by 7 xu, that we get as y2 value as 25 into 25 divided by 21 xu. So we got y1 and y2 value. Just to substitute in this formula to get the point or the distance from the compressive fiber or the utmost compressive fiber at which the compressive stress is acting or the compressive force is acting. So that is nothing but C1 y1 plus C2 y2 by C1 plus C2. So what is C1? This is the C1. This is the C2. So y1 y2 we got. On substituting here, we get a value as 0.6 xu. So this is the value of y bar. But as per IS 456, this y bar will be 0.42 xu. That we have already seen in the previous question. But here, because of considering stress variation as a straight line instead of parabolic, we got y bar as 0.6 xu. This is a variation. So this is how we have to proceed with the question like this. Whenever the stress block parameter or the stress variation is different from the IS total provisions, we have to follow like this. First, we have to um, consider the similar triangle concept, and then move on to uh, finding the depth of the sections, and move on to find the compressive force and equate with the tensile force so that we can get the answer for xu. And moving on to y1 and y2, we can get the y1 y2 by using a CG concept. So that is the theoretical observation. We can get how to calculate the xu1 y bar. Now we shall move on to the next question. This is a doubly reinforced beam. A doubly reinforced beam has effective cover D dash for compression reinforcement. So for compression reinforcement at top of the section, the cover is D dash and small d for tension reinforcement. Or actually this small d is nothing but the effective depth, not for tension reinforcement. This is absolutely not correct. This d is the effective depth of the beam. So here mentioned clearly. And we have to calculate the maximum strain in concrete at the level of compression reinforcement. How to derive that, or what is the formula of maximum strain in concrete at the level of compression reinforcement? So options are given. Choose the best answer. D dash is nothing but the cover for compression reinforcement, and XU is the depth of neutral axis from the extreme compression fiber. And here option A is correct, 0.0035 into 1 minus d dash by xu. Now we shall see some more points in detail. So how we are getting this relation? So nothing but epsilon SC, that is strain in compression steel, divided by xu minus d dash. Here also a similar triangle concept only is followed. Strain here is divided by this distance. What is this distance? Xu minus d dash equal to strain in compression concrete, or the utmost compression fiber in concrete, divided by Xu. So we know what is epsilon Cu, that is 0.0035 into 1 minus d dash by Xu, that is Xu minus d dash by Xu is nothing but 1 minus d dash by Xu. So this is how we are arriving this relation. Now we shall see more points apart from this. Compressive stress in concrete is given as Fc is equal to 0.45 FCK. In case of doubly reinforced section, how to get the compressive stress in concrete? That is given by 0.45 FCK. And stress in compression steel, how to calculate that? FSC, that is stress in compression steel, is calculated at the strain level, that is epsilon SC. So that is that we can calculate by using this relation. So at this strain, what will be the FSC value? We have to calculate that. The maximum strain in extreme fibers for steel is given by using this formula, 0.002 plus 0.87 Fy by ES. This formula we have already seen in the previous question. So here for various stress level, there will be a corresponding strain level. So how to calculate that? For 0.80 Fy stress level, for example, we are calculating the strain for 0.8 Fy stress level. For example, this. Actually, Fy is nothing but 415. For example, we are considering Fe 415 steel grade, then Fy is 415, then 0.87 Fy will be like this, and zero point 0.8 Fy and 0.9 Fy, 0.9 Fy, 0.97 Fy. This at this stress level, we can calculate corresponding strain. For example, we can see this 0.8 Fy now. For 0.8 Fy stress level, strain is 0.00144. How? Here just substitute 0.002 plus 0.87 into 0.8 into Fy. Are you getting it? 0.87 into 0.8 into Fy divided by ES. So we know Fy as 415, ES is 2 into 10 power 5. So on substituting all the relevant details here, we can get the strain value as 0.00144 for Fe415. It will vary for other grades of steel. For example, Fe500, the strain will be different. And the stress corresponding to this strain is simply 0.8 into 0.87 Fy, because we are calculating at stress level 0.8 Fy. So that's why stress is 0.8 into 0.87 Fy, that is nothing but 288.84 megapascal. Why this calculation? We shall see now. By interpolating, we can get the value of FSC at ESE. How? We can see in this table. For strain level 0.00144, stress is 288.7. This calculation we have seen as an example. Similarly, we can do the calculation for other stress levels like 0.85 Fy, 0.9 Fy, 0.95 Fy, and 0.975, and finally the Fy value. So we can get a table like this, and for corresponding strain value, for example, the strain value, this epsilon SC is 0.00275, then we can interpolate the value between these two, so that we can get the stress value as FSC. By interpolating this table, we can get the value of FSC, that is the compressive stress in steel, to the corresponding the strain in compression steel, that is denoted as epsilon SC. For example, epsilon SC is 0.0025, then somewhere between 0.00241 and 0.00276 the strain is lying. Then correspondingly we have to interpolate between these two stress level, so that we can get the value of FSC. If at all in the question they have not mentioned the value of FSC, then we have to calculate like this only. So in this question we have learned about the compression strain, or the strain in compression steel, that we can get using this formula, and compression stress in concrete using this formula, FCC is equal to 0.45 FCK, and stress in compression steel is calculated at corresponding strain. How to calculate that strain? We can get using this stress levels. or if at all they have given the strain value, or we can say like that. So correspondingly we have to calculate this FSC according to epsilon SC that we have calculated in this relation using d dash by d dash and xc values. So by interpolating the things we can get the value of FSC. Now let's move on to the next question. This question is also based on a doubly reinforced section. A doubly reinforced beam section is 250 mm wide and 450 mm deep. Effective depth is given as 450 mm. It is reinforced with two numbers of 16 mm diameter bars as compression reinforcement, which having the compression reinforcement cover as 50 mm, that is D dash value, and four numbers of 25 mm bars as tension reinforcement. We have to use M20 grade of concrete and Fe250 grade of steel. Not the grade of steel here, Fe250. Then what will be the ultimate moment of resistance? So we have already seen the moment of resistance calculation in case of singly reinforced beam. Now we shall see the calculation for moment of resistance for doubly reinforced beam section. Let's see the calculation part. Here they have mentioned as Fe250 grade of steel. Then the FSC value shall be nothing but 0.87 Fy. If in the question they have mentioned the steel grade as Fe250, or when both the compression and the tension steel yielding at same time or yielding, then FSC value shall be got simply like 0.87 Fy. In the previous question we have seen how to calculate FSC value in case both the conditions are not prevailing. If any of these conditions like Fe250 steel is used, or when both compression and tension steel is yielding, then FSC, that is compression or the stress in compression steel, that is FSC, shall be nothing but 0.87 Fy. So here Fy is 250. 250 into 0.87 gives 217.5 megapascal or Newton per mm squared. So simply we can calculate FSC value. Now let's move on to the moment of resistance and how to calculate that. So before moving to moment of resistance, we have to find XU, as we have already seen in the singly reinforced. Here also we have to find the XU, that is the depth of neutral axis from the compression fiber of the concrete. So 0.36 FCK B into XU plus FSC minus 0.45 FCK. This 0.45 FCK we have seen as a FCC value in the previous question. That is the same thing followed here, into ASC equal to 0.87 FY AST. So upon substituting all the things over here, FCK is 20, B is nothing but 250, XU that we have to calculate by using this relation, FSC 217.5 megapascal, or just 217.5, 0.45 into 20 into ASC. What is ASC? They have mentioned two numbers of 16 mm bars as compression reinforcement, that is nothing but 2 into pi by 4 16 square, that is the ASC value, and 0.87 into Fy here is 250 into AST. What is AST? Area of tension reinforcement. They have mentioned four numbers of 25 mm bars, so that means 4 into pi by 4 into 25 square. So upon substituting all the parameters here, we can get the answer for XU as 190.67 mm. So that we have to always compare with the XU limit. Whenever we got XU value, that value has to be compulsorily compared with XU limit, that is the XU for balanced section. Then only we can say the section is over reinforced or under reinforced or a balanced section. The beam should always be an under reinforced section. So that is the prime criteria. It should not be over reinforced. If at all it is over reinforced, then failure will happen in a tragic way. So that's why under reinforced section is always used. Here XU limit is 0.53D. How? Because we are using Fe250 steel. Fe250 steel grade, we have to use XU limit is equal to 0.53D. We know what is D value. Effective depth is 450. 450 into 0.53 is 238.5 mm. So the actual XU value is less than the limiting XU value. Then that means the section is under reinforced. then we can proceed with the calculation of mu, that is ultimate moment of resistance. So 0.36 FCK BXU into this lever arm distance, that is d minus 0.416 XU or 0.42 XU, plus the compression steel part, the FSC minus 0.45 FCK into ASC into d minus d dash is the lever arm distance for compression steel. So simply substitute all the things so that we can get the mu value as 160.89 kilonewton meter. So this is the basic formulas and basic things regarding doubly reinforced section. Whenever we get doubly reinforced section, we shall use these two formulas. One is this and another one is this. One is for XU finding to find the XU value. Another one is to find the mu, that is ultimate moment of resistance value. Now we shall see some more points regarding doubly reinforced beam. Doubly reinforced beam is uneconomical when compared to singly reinforced beam because the compressive steel is not stressed up to 0.87 Fy. This we have already seen in the second question indirectly, because whenever we are using steel grades other than 250, and whenever both the steel that is not yielding, that means the compressive steel is not used to the fullest. So that means there will be a wastage of steel material in the compressive section. So that is why doubly reinforced beam is uneconomical. Whenever we are stressing the compressive steel up to 0.87 Fy, as we have seen in this formula or in this problem, then that will be some sort of economical. But in not in all case we can get this Fe250 or when both the steel yielding. So that is why doubly reinforced beam is uneconomical compared to singly reinforced beam. Only because the compressive steel is unused. That is, it is not stressed up to its limit of 0.87 Fy. And next point is doubly reinforced beam provides safety against reversal of stresses due to wind, seismic forces, temperature stresses, etc. So it will provide some safety against this reversal of stresses, that is horizontal forces due to wind, seismic forces, temperature stresses. So we can withstand these type of stresses by providing doubly reinforced section when compared to singly reinforced sections. Now we shall move on to the next question. The limiting percentage of tension steel reinforcement of beam having M20 grade of concrete and Fe 500 grade of steel is. So what is the maximum percentage of tension steel reinforcement that has to be provided in a beam section which is having M20 grade of concrete and Fe 500 grade of steel as a tension reinforcement? What is the limiting or the PT limit value? Here the answer is option D, 0.957%. There is a simple but important formula to find this PT limit. That is the limiting percentage of tension steel reinforcement is given by 41.61 into FCK by Fy into XU limit by D. So FCK is given as M20 or 20 Newton per mm square, Fy is 500 and XU limit by D is corresponding to this Fe 500 value. So we shall see here now. This table is given as per IS 456 and XU max by XU max by D shall be 0.0035 by 0.002 plus 0.0035 plus 0.87 Fy by ES, or on simplification by using this ES value as constant like 2 into 10 power 5, we can get like this equation also. XU limit by D is equal to 700 by 1100 plus 0.87 Fy. So upon substituting Fy value as 500 over here, we can get XU limit by D as what? 0.46, as you can see in this table. We can remember these three values so that we can use as it is, so that we can get rid of this formula. But for just the sake of mind, XU limit by D is equal to 700 by 1100 plus 0.87 Fy is the basic formula to determine the ratio between XU limit by D. So here XU limit by D is 0.46 because Fe 500 grade of steel is used. So upon substituting all the things, we can get the limiting percentage of tension steel reinforcement is 0.957%. Now we shall move on to the next question. Consider a continuous beam of T section of length 3000 mm. The effective width of the flange having 300 mm web width and 100 mm flange depth is. Here they have mentioned as continuous beam of T section having length of 3 meter or 3000 mm and the width of the flange or the effective width of flange, that is nothing but small b value as 300 mm, and the width of the flange we have to calculate having 300 mm web width. The width of the web is given as, that is bw is given as 300 mm, and the flange depth, that is d suffix f, is given as 100 mm. So we have to calculate the effective width of flange, that is b suffix f. So here the answer is option C, 1250 mm. We have to use this formula, that is effective flange width of T beam is given by using this relation, BF is equal to L naught by 6 plus BW plus 6 TF. So what is L naught here? L naught is the distance between points of contraflexure or the points of zero moments, and 0.7 L in case for continuous beams and frames. Here they have mentioned clearly as continuous beam, so that is why L naught is equal to 0.7 into 3000. So 0.7 into 3000 divided by 6 plus BW, that is 300 plus 6 into DF. DF is 100. So upon substituting all the things, we shall get the answer as 1250 mm as the effective width of flange, that is BF. This is in case of T beam. In case of L beam, how to calculate that? BF is equal to L naught by 12 plus BW plus 3DF. And in case of effective flange width of isolated T-beam, then BF is equal to L naught by B plus 4 plus BW. And in case of L beam, like this, BF is equal to 0.5 L naught by B plus L naught by B plus 4 plus BW. So these four formulas regarding effective flange width of flanged beams. These four formulas are important to calculate effective flange width of corresponding beam sections. And L naught is the distance between points of contraflexure or points of zero moments, or in case of continuous beams and frames, it shall be 0.7 into the effective length. Now we shall move on to the next question. The expression for equivalent depth of flange, that is YF, for a constant compressive stress is based on Marcus stress block, option B Gersov stress block, option C Whitney stress block, option D Rankine stress block. Because of parabolic variation in the stress block, we have to convert that parabolic stress variation into rectangular so that the calculation will be more easier. So in order to convert parabolic variation of the XU or the depth of neutral axis up to the parabolic variation, we shall consider the YF. This is given by Whitney stress block. So YF formula is given as YF is equal to 0.15 XU plus 0.65 DF. This is the YF formula, that is equivalent depth of flange in case of flanged beams like T and L beams. And this 0.15 and 0.65 are the constants that is based on these conditions. When DF is equal to 0.43 XU, then YF is equal to 0.43 XU. If DF is equal to XU, then YF is equal to 0.8 XU. On the basis of these two conditions, this A and B value are derived as 0.15 and 0.65 respectively. What is DF? DF is the depth of flange section. And the depth of constant portion of stress block is when df by d is greater than 0.2. Whenever the depth of flange to the effective depth of the beam section is greater than 0.2, then the depth of constant portion of stress block, that is the rectangular variation, this is the constant portion of stress block, will be under the flange portion only. What they are mentioning is, for example, this is the T section, consider this as the T section. The depth of constant portion of stress block, that is this one, and then only this is varying like parabolic. This portion will be in within the flange section of the T beam when if and only if df by d is greater than 0.2. This is the concept. We shall see more details on T-beam and T-beam calculation of moment of resistance in the next question. So this question purely deals with the T-beam section, a section of monolithic slab beam assembly. A section of monolithic slab beam assembly has following particulars. The slab thickness is mentioned as 100 mm, that is this one. The slab width is mentioned as 1100 mm, that is this one, BF. The beam depth is 400 mm. This is the beam depth, that is 400 mm. Beam width is 300 mm. This is the beam width. The reinforcement is provided as 4 numbers of 25 mm diameter bars and 3 numbers of 16 mm diameter bars. So 2 layers of reinforcement are there. In one layer 4 numbers of 25 mm. In another layer 3 numbers of 16 mm. The cover is given as 50 mm. We have to use M20 concrete grade and Fe415 steel grade. What will be the moment of resistance of this T section? T section is nothing but the monolithic slab beam. For the slab thickness, it is given as 100 mm. That is nothing but the flange thickness of T beam. It is analogous to T beam. We have to consider like that. Let's see the steps to calculate the moment of resistance in this problem. So how to proceed with the step by step? Let's see that. So first step, we have to assume the EXU, that is the depth of neutral axis, is lying within the flange. Then what will be the calculation? It is nothing but the rectangular beam. So whatever the calculation we are following in the rectangular beam, the same approach has to be followed. Simply 0.36 FCK BF, because we are considering breadth of flange, that's why BF into XU equal to 0.87 FY AST. Here we know all the things. FCK is 20, BF is slab with us 1100 mm, and XU we have to find 0.87 into FY is 415 and AST is 4 numbers of 25 mm and 3 numbers of 16 mm. So total AST we have to find and substitute here and find the XU value. That is, we got this as 117 mm, which is greater than DF. So DF, that is slab thickness, here mentioned as 100 mm, but here we got XU as 117 mm, that is beyond the DF level. So that means our assumption is wrong. What is our assumption? The neutral axis is lying within the flange, like here in this diagram you can clearly see. But the assumption is wrong as per the given particulars. So let's move on to the next step. So then assume DF is less than 3 by 7 XU. So in the first step we have assumed XU is lying within the flange, but that assumption got wrong. Now let's move on to the second assumption. DF, that is the depth of flange or the thickness of flange, is less than or equal to 3 by 7 XU, and calculate using this relation. In case we are assuming like this, we have to use this relation to find the XU value. So 0.3 FCK BW. Here we have to be careful in providing the width of the section. Here BW is given into XU. Because why BW? Because we are considering the depth of the neutral axis in the lying in the web portion. That's why BW into XU plus the flange portion 0.45 FCK into BF minus BW. Here minus BW because we have already considered BW here. So that's why cancelling out BW value by subtracting it from the BF value. So into DF equal to 0.87 FY AST. So this is the basic formula when we have to assume when we are assuming DF is less than or equal to 3 by 7 XU. So upon substituting FCK 20 BW as what is BW here? Beam width is given as 300. XU we have to find 0.45. FCK is 20. BF is 1100. BW is 300, and DF is 100. So upon substituting all the things, we get XU value as 95.65 mm, which is again less than DF. So this assumption is also wrong. If XU is less than DF, that means the neutral axis depth is lying within the flange itself. But in the first assumption itself, it got wrong. Then how it will be correct? So the second assumption is also got wrong. So moving on to the third assumption. So before moving to third assumption, we shall see this formula in detail by using this diagram. Here you can see this is a stress diagram and this is a BF minus BW part. Here we have mentioned here because we have assumed BW here. So in order to cancel out BW part, we are subtracting minus BW. So this is the section and stress diagram. Accordingly, we have to calculate. Now moving on to the next assumption. Next assumption is DF is greater than 3 by 7 XU. Then how to calculate, then what is the relation we have to follow? The same relation as we have seen in the previous step, but only thing is DF has to be substituted as YF. And what is YF? YF is the equivalent depth of a straightly varying portion that we have seen in the Whitney's block in the previous question. What is YF? YF is 0.15 XU plus 0.65 DF. So just change the df into yf, then find the value of xu. Here we have got xu as 141.57 mm, which is greater than df, and again this assumption is also satisfying. Df is greater than 3 by 7 into 141.57. So that means finally this assumption is correct. So we have calculated the XU of this given section of T beam. Then finally we have to calculate the MOR, that is moment of resistance. That is nothing but 0.36 into FCK into PW XU into D minus 0.42 XU plus 0.45 FCK into BF minus BW YF into D minus YF by 2. This is simply nothing but the relation followed here. The relation here, that is 0.36, are the parameters here. Simply drop it here and multiply this with the lever arm distance, and again this value here 0.45 fck into bf minus bw yf into the lever arm distance is d minus yf by 2. So we can get the answer for moment of resistance uh, in case of this step. What if we got the correct value in the second step itself? Then simply we have to find the moment of resistance as 0.36 fck bwxu into d minus 0.416 xu plus 0.45 fck bf minus bw df into d minus df by 2. Actually simply interchange yf with df. That's it. Uh, that is the main thing we have to follow. In case we got the assumption in the step 2 itself, this assumption itself, then yf has to be interchanged with df value simply. In case we got the assumption in the first step itself, then simply go with the rectangular moment of resistance formula, that is nothing but 0.36 fck bf xu into t minus 0.416 xu, as we have seen in the first second question. Simply we have to move with rectangular beam formula. So these are the assumptions and the procedure steps to find the moment of resistance in case of T beam. Now we shall move on to the last question. For a doubly reinforced beam, the percentage tension reinforcement is given as 1.37. The limiting tensile reinforcement is given as 0.961%, and FSC value, that is the stress in compression steel, is given as 351.9 megapascal. Now we have to calculate the minimum percentage of compression reinforcement, and they have mentioned the grade of concrete as M20. This is also a simple question. You have to follow one formula, substitute all the details in that formula to get the answer for minimum percentage of compression reinforcement, as we have seen in the limiting reinforcement in case of tensile reinforcement. So here the option C is correct one, 0.431%. What is the formula? Here you can see PC star, that is the minimum percentage of compression reinforcement, that is the limiting value of compression reinforcement, as we have already seen the tensile reinforcement. Similar to compression reinforcement, we shall see now. That is equal to 0.87 Fy into Pt minus Pt limit divided by Fsc minus 0.45 Fck. We know all the values, like Fy is nothing but 415, Pt is nothing but 1.37, PT limit is 0.961, FSC is given as 351.9, and FCK is 20. Actually, FY is not mentioned here, so let FY be 415. That is FY 415. So upon substituting all the values here, we can get answer as 0.431 is the minimum percentage of compression reinforcement. And let's see another point. If PT value, that is the percentage of tensile reinforcement provided, is greater than the limiting percentage of tensile reinforcement, and the percentage of compression reinforcement is greater than 0, then in order to avoid over reinforced section, PC shall be greater than PC star. That is, the provided percentage of compression reinforcement should always be greater than the limiting reinforcement percent. This is the concept. We have to provide more reinforcement in the compression section in order to avoid over reinforced section, so that we can get an under reinforced section or the under reinforced beam. So we have seen all the formulas of moments of resistances, and how to calculate neutral axis in case of other stress block parameter or other stress block diagram, and how to follow IS 456, what is the exit limit value. Accordingly, we have to calculate the Fy and Fe values. So we have seen some of the most important thing in case of limit state method that we can expect in the examinations. So I request you to view the video of summary of IS 456, so that you can get more clarity on IS 456. What are the important things we have to be aware of, like what is the minimum tensile reinforcement, how to calculate that, what is the maximum tensile reinforcement, like that we can get from IS 456. That is already dealt in the summary of IS 456 2000 video. You can watch it right now. You can get some more insights about it. And thank you for watching this video. Please subscribe the channel and share with your friends. Thank you.